Hi everyone, welcome back. In this video, we're going to talk about some strategies and techniques to approach trigonometric equations under different circumstances. The first type of question is collect like terms. So the first question we're going to deal with today is the following. Cosine x plus square root of 3 is equal to negative cosine x. So how do we approach this one? So we should first recognize that we could move the negative cosine x on the right side over to the left side. So we will have something like cosine x plus cosine x plus root 3 is equal to 0. And if we combine the like term, which is the 2 cosine x, we would have 2 cosine x. And if we plus root 3 is equal to 0. And if we move the square root of 3 over to the right side, we would have negative root 3. And then divide 2 on both sides, we would have negative root 3 over 2. And from here, we could then use our friend, the cast rule. Because cosine is negative, that means this angle, the x, if it's in standard position, must end up in quadrant 2 or 3. So x, we would have the reference angle in this case, it will equal to 30 degrees or pi over 6 in radian. And if it's in quadrant 2, then we would have 5 pi over 6 plus 2n pi, where n is an integer. And if it's in quadrant 3, then we would have x is equal to 7 pi over 6 plus 2n pi, n is integers as well. So by using these two generalizations, we would have the overall solutions for this equations right here. So this is how we can combine like terms, and then we can solve the problem. Next question, or type of question, is factorization. So we can factor something out first, and then attempt to solve the equation. So a very tempting approach that many students will take for this type of question is to divide sine theta on on cosine theta in this case, cosine x theta in this case, on both sides. So we can cancel this, so we will have 2 sine theta is equal to 1. However, by doing so, we are automatically assuming that cosine theta cannot be 0, but that is not specified or implied in the question itself. So what we should do is we should start off by moving the cosine x on the right side to the left side. So we would have this. And then we need to recognize that we could factor the cosine out from the left side. So we can do cosine theta 2 sine theta minus 1 in bracket is equal to 0. And from this step forward, we can use zero product law, which is to say, so we have the product of two terms is 0, and so there are two possibilities. The first possibility is that cosine theta is 0. We would have theta will be equal to pi over 2 plus n pi, and this integers. Because still, go back to our cast rules. We know that cosine pi over 2 is 0. That is here. That is when the angle is right here. So when when the angle is cosine 3 pi over 2, that will be also be 0 as well. So this would be a generalization, a valid generalizations for this particular scenario right here. And next, the second possibility is that the second term is 0, which is to say that the 2 sine theta minus 1 is 0. So sine theta will be equal to 1 over 2. And the reference angle right here for this one would be pi over 6, or 30 degrees. So since sine is positive, we could have it in the quadrant 1 or quadrant 2. So we can do quadrant 1. It is pi over 6 plus 2 and pi, which is a full revolution, and then it's an integer. And when the angle is in quadrant 2, we would have 5 pi over 6 plus 2 and pi, and as integers as well. Next type of question is factor quadratic type. So what if we have a relatively more complex or seemingly complicated equation like this? So we have 2 sine squared x minus 3 sine x plus 1 is 0. So we should recognize that we have lots of sine x, or only sine x actually, in this equation. And we should notice that if we have a sine x, a sine squared x, that is simply saying that it's sine x squared. So we can start off by assigning a variable to represent sine x. And then we substitute this variable back into the original equation. We would have 2a squared minus 3a plus 1. We would have 0. And then if we factor this using regular quadratic functions strategies, we can simply figure this out by using inspections. So we would have 2a minus 1 times a minus 1, which is equal to 0. And we need to recognize that this a is actually the sine x. So if we substitute that back, we would have 2 sine x minus 1 times sine x minus 1 is equal to 0. And now we can apply the zero product rule again. So we would have two possibilities again. The first possibility is that 2 sine x minus 1 is 0. Sine x is 1 over 2 again. And x would be equal to, again, pi over 6 plus 2 and pi, and its integers, or 5 pi over 6 plus 2 and pi, and is still integers. If we have questions about how I came up with this generalization, you should roll back and watch this part again. The second possibilities in this case would be when sine x minus 1 is 0, which is the second term here. So we're really just classifying these two different scenarios. In this case, sine x will be 1, and x would be pi over 2 plus 2 and pi, and its integers. Be careful that this is different to cosine, that when we're talking about sine, when x is equal to pi over 2, it is 1, and when x is 3 pi over 2, it is actually negative 1, so that is not right. So for this type of questions, we are using a variable to represent a certain trig functions, or we can simply view this trig function as a whole unit. So 2 big block squared minus 3 big block plus 1 is 0. So we can factor this using inspections or other methods, and we can figure out the solution. The next type of question is rewrite with a single trig function. So our example here is 3 secant squared x minus 2 tangent squared x minus 4 is equal to 0. So here, we need to apply a little identity right here. So the identity that we're going to be using is secant squared x is equal to 1 plus tangent squared x. So if we apply this, or by substituting 1 plus tangent squared x for secant squared x in this question, we would have 3 bracket 1 plus tangent squared x minus 2 tangent squared x minus 4 is 0. And if we remove the bracket by multiplying 3 to both terms inside the bracket, we would have 3 plus 3 tangent squared x minus 2 tangent squared x minus 4, which is 0. And if we combine like terms, simplify the whole equation right here, we would have a tangent squared x minus 1 is 0, and tangent squared x is 1, and tangent x is positive and or negative 1. So if we look at this, we would have x would be equal to pi over 4 plus n pi, and this are integers, or 3 pi over 4 plus n pi, and is integers. Essentially, how I came up with this generalization is we know that a tangent pi over 4 is 1. So this is a reference angle. So if we draw it on a Cartesian plane, we can have 45 degree, pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. And we can rotate them for 4 revolutions each. And we need to recognize that for this, we can only use these two is sufficient enough. So if we apply this one and rotate half a period each time, we can cover all the possible angles, which is n pi. If we use this angle and rotate half a period each time, we would cover all the configurations for tangent x, that is 1. Or plus negative 1. So the reason why we are covering 4 configurations and not caring about cast is because we have positive and negative, both signs are covered in this case. So this is how we can rewrite the equation using the single trig function. And the intent and the purpose behind that is because it's quite hard to deal with secant and tangent at the same time. So we want to reduce to one single trig function. The next method or type of question is square and then convert. So why do we want to square and convert is because right now we only have sine plus 1 and cosine. And as I said previously, it is fairly difficult to deal with sine and cosine at the same time in the same equation. So we want to reduce them into one single trig function. So how do we do that? That definitely involves some applications of identities. But as we know that for a fairly amount of identities involves the usage of some trig functions squared. So we want to start off by squaring both sides like this. So we want to do sine squared plus 1 plus 2 sine theta is equal to cosine squared theta. So we have artificially created some squared terms right here. And if we see a squared terms like sine squared, cosine squared, we should think about the identity sine squared theta plus cosine theta, a squared theta is 1, cosine 2 theta is cosine squared theta minus sine squared theta, or other identities as well. So these are not necessarily used in this case. However, it's a good start point for us to think about various possibilities. And then what we should do is then we should move this cosine squared theta on the right side to the left side. So we'd have sine theta squared minus cosine theta squared is equal to, or actually, let's move the sine theta on the left side to the right side, excuse me. So we'd have 1 plus 2 sine theta is equal to cosine theta minus sine squared theta. And as we recognized, we can implement this identity right here. So we would have 1 plus 2 sine theta is equal to sine 2 theta, double angle identity. And we should also recognize that we still have two trig functions here, sine and cosine. So we want to reduce that to 1. So we can use the identity that cosine 2 theta is equal to 1 minus 2 sine squared theta. So by implementing that, we would reduce everything into only sine theta. And then we can cancel the 1 out, and we can move the 2 sine squared theta to the left side. So we would have 2 sine squared theta plus 2 sine theta is equal to 0. Divide by 2 on both sides. We would have sine squared theta plus sine theta is 0. And we can factor 1 sine theta out. And inside the bracket, we would have sine theta plus 1 is equal to 0. So still two possibilities using the zero product law. The first one is sine theta is 0. Then we would have theta is pi plus n pi. N is integers. Sorry, it is actually, because as we know that sine 0 degree or radian is 0, and it can flip half a period on the Cartesian plane, so we would actually have n pi itself, and this integers. And the second possibilities would be sine theta plus 1 is 0, sine theta is negative 1. So theta would be 3 pi over 2 plus 2 n pi. N is integers. So these are the possible solutions for this equations. And let's go back and check, are there any extraneous solutions, or are there any inherent restrictions in these equations? And it seems like there's no apparent restrictions in this case. So that's how we can figure out this equation using two identities and the strategy of square and then convert. So for this question, it is probably the most difficult questions that's going to be covered in this video. I hope you find these walkthrough and solutions helpful, and thank you for watching.